In this video, I'm going to go over how you classify either ionic or covalent bonds, and then I'm going to go over oxidation number, and this will include some polyatomic ions as well. So if you want to classify bonds as either ionic or covalent, you have to pay attention to whether you're working with metals or nonmetals. Remember, there is this step ladder on the periodic table, and everything to the left of the step ladder are metals, everything to the right are nonmetals, and there are some exceptions here that are called the metalloids. We're not really going to worry about these too much, but they fall on that step ladder. They're all metalloids with the one exception of aluminum. If you test the properties of aluminum, they are purely metallic, where metalloids have an odd mix, and it varies from one metalloid to another, where they will have properties that are some metallic properties and then some non-metallic properties. For this, I'm going to ignore the metalloids for now. If you want to classify bonds as either ionic or covalent, there's a couple of easy ways to do this. If they contain a metal, they are going to be ionic. So for example, if you have something like sodium chloride, sodium is here, that is a metal, and chlorine is a non-metal, so that is ionic. Or you can have calcium chloride, or you can have sodium fluoride. It's really any combination of any metal from the left-hand side of the periodic table with any non-metal. And they can vary a lot. It doesn't always have to be a halogen. They're just the ones that I came up with. So for example, you can have sodium oxide, because oxygen is a non-metal. But if you see a metal in the compound, they are going to be ionic. Now, covalent means they are two or more nonmetals. So you can have fluorine bonded to oxygen or nitrogen bonded to oxygen. So you can have like N2O5, or phosphorus is in there, P2O3. You can have any combination of nonmetals, and those are going to be covalent. Now, some other things that will come up are the polyatomic ions. And the sheet that I gave you, this is on the other side of it. So the polyatomic ions, as the name implies, they would form ionic bonds, because it says ions here. Now, most of these polyatomic ions are nonmetals that are bonded together, but every once in a while you'll get a metal like manganese, and then there's some that will be chromium that are down a little farther. And they are still making these polyatomic ions. But what happens with the polyatomic ion, it's like this whole thing in all of these examples is acting almost like it's a single element, right? And it goes for all of these. So hydroxide is one that will get used a lot. So for example, you can have sodium hydroxide. Now there's two reasons why you'd be able to pick this out as an ionic compound. One is sodium is a metal, and the other one is OH is a polyatomic ion. It is hydroxide. And that goes for any of these polyatomic ions. Like I said, most of them are nonmetals that are bonded, but every once in a while you get metals like the chromium and the manganese in this example. So if you see a metal, no matter what, it is ionic. If there's a polyatomic ion, it is also going to be ionic. Most of the time, the compounds that contain polyatomic ions will also have a metal, but there is an exception down here, and it is this NH4, this ammonium, because this is the only one that's positively charged. Just like most metals have a positive oxidation number, which I'll get into next, ammonium also has a positive charge. So you could have something like NH4OH. That's ammonium, this part of it, and then OH is hydroxide, which I talked about just a second ago. Now, there's no metal in there, right? So when you first look at that, you might think that is a covalent compound because there's no metals listed. But this polyatomic ion is basically acting like a metal would act. It has a charge. It has a positive 1 charge. And this hydroxide has a negative 1 charge. So you're working with these two ions. And since you're working with ions, you get an ionic bond. There is electrons that were transferred here, and then since these two charges are opposite, they end up sticking together kind of like a magnet would. All right, so a couple of things here. If a compound or molecule, whatever it is, if it contains a metal, it is ionic. If it is just nonmetals, it is covalent, with the exception of this ammonium polyatomic ion. You can get a polyatomic ion in here without a metal. Most of the times they do. So if you have like magnesium phosphate, right, something like that, magnesium bonded to the phosphate group, right, it's clear that this is a metal, so you would pick out ionic, but the other way you could tell is PO4 is a polyatomic ion. All right, so that's how you classify these. Now I want to get into oxidation numbers, another thing we talked about recently. So to figure out oxidation numbers, you're really just thinking about whether these elements on the periodic table are gaining or losing electrons to become more stable. So the alkali metals, this first column here, the example I was using in class is sodium here, for example, can either gain 7 electrons to achieve a noble gas configuration like argon, or it can lose 1 electron and end up with an electron configuration similar to neon. Remember, everything is going to bond to try and get a noble gas configuration, basically meaning their valence shell of electrons will be full. So sodium will tend to lose 1 electron because it's a lot easier to lose 1 than gain 7. So when it loses an electron, it ends up with a positive 2 charge. Beryllium, this second column here, they will lose 2 electrons. So magnesium, for example, will lose 2 electrons to become like neon. It's a lot easier than gaining 6 to be like argon, so that's a positive 2. The transition metals we skip for oxidation numbers. Now, it looks kind of blurry on my screen when I'm doing this, but when you look at your periodic table, there are these little numbers in the upper right-hand corner of a lot of these elements. And what happens is they are referred to as polyvalent. They can move their valence electrons around and they can end up with more than 1 possible oxidation number. So copper, for example, can be +2 or it could be +1. It depends on what it's bonding with, what kind of compound it's making, that it's going to be either a +2 or +1. Chromium can be +6 or it could be +3 or it could be +2. So when we're counting oxidation numbers, we skip the transition metals because they behave kind of odd, right? But they have these numbers here. So zinc, for example, can only be a +2. That's why that's the only number written there. By the time we get to boron, boron can lose 3 electrons to be like helium, or it can gain 5 to be like neon. So when it loses 3 electrons, because that's easier than gaining 5, it ends up with a +3 charge. Carbon's right in the middle. It can either add or lose 4, so you end up with a plus or -4. Depending on what it's bonding with, will depend on whether it's +4 or -4. Now nitrogen, you're getting to a point here where these elements, they can gain 3 electrons. Otherwise, they'd have to lose 5. So now you're at a point where it's easier to gain 3. So that ends up with a -3 charge. Oxygen only has to gain 2, so that's -2. And the halogens only have to gain 1, so they're -1. Now, the oxidation numbers, this +1, +2, +3, +-4, -3, -2, -1, this is going to end up getting used a lot when we start talking about chemical reactions and naming compounds and figuring out what the compounds will be when we write out their formula. This is going to be an important concept that we are going to use in this course throughout the rest of the chemistry portion.